Okay, so we're picking up because I accidentally hit stop. So if I'm consistent, I did note, I changed that to force of gravity. So I've just listed, you won't have to do all these intermediate steps forever, but it's a good place to start. So now I'm ready to put in some numbers. And I have sum of forces on the y equals, well, force of the floor is 261 newtons up, plus, and we said force of Hannah, that was 511 newtons, and I'm going to bracket that, times sine of 39. Wow, and that looks too much like an S. 511 newtons times sine of 39 minus, and my force of gravity is also 261 newtons, and that's going to be down. And I'm going to make a note that that's up. Let's get a number for. Okay, so what do we have for a raw number for force of Hannah upward? 321.58. Yeah, 321.58 and change. When we add it to the force of the floor, what we get is 582.58 blah 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 newtons upward minus the 261 newtons downward. So we have a net force on this thing, sum of forces on the y. Oh, duh. Well, that was silly. 321 point blah 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 blah. Okay. Well, I should put in the 0.58 blah 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 newtons, and that's upward. Why did we have to include force of Hannah on our sum of y? Sum of forces y? Yeah. She might be pulling on this object with a string attached to it. Maybe she's been shrunk and she's pushing from a low position and Ireland's pulling or pushing on the other side. We don't know what the actual situation is, but she's exerting some force on the y-axis, so that's why we have to do that. Let's get our sum of forces on the x. Okay, so my sum of forces on the x is going to be all my forces to the right minus all my forces to the left. What do we have to the right? Well, we have force of Hannah on the x. And on the left, we have force of Ireland. Do we have to resolve Ireland's force? No. As far as we're told that it's a 0-degree axis, or 0-degree angle, it's on the x-axis. So force of Hannah on the x, of course, is going to be force of Hannah cosine theta minus force of Ireland. Who wins this tug of war? That's our question. You get something along the lines of 99 newtons. So 99.12, blah, blah, blah. How many sig figs do we have? Ooh, 2. We're limited by that stupid angle. So we get 99 newtons to the right. And I just shorthanded it by doing the arrow. These are not hard. They're just bookkeeping. We're just looking for net forces. Okay, so Derek leaves his physics book on the top of a drafting table inclined at a 35-degree angle. Now, they gave you a free body diagram. Of course, that's not usually the case. Free body diagram shows the forces acting on the book, find the net external force acting on the book, and determine whether or not the book will stay in position. And the free body diagram they give us looks like that. We do a lot of objects on slopes, and so you do have to get used to that. We'll start doing some weird things with the x-axis in a little while, but we're not going to do that yet. So, as always, start off with sum of forces on the x, sum of forces on the y, and the sum of forces on the x is going to be... Now, here's the weird part. Well, okay, no, we're not shifting the axis yet, Moser. I'm going to go ahead and do that, okay? I'm so used to shifting the axis, I almost did it there. So all the forces, no, you know what, we are going to shift the axis. Dagnabbit. Okay. Okay, so now if we look at this real quickly, with the axes aligned the way they are, how many forces do we have to resolve into their component vectors? 2. both the force of friction, which runs along the plane of the table, and the force of the table on the book, which is directly, and we'll talk more about normal force when we get there, it's directly perpendicular to the table. We can do this weird thing with slopes where we shift the axis like that, and guess what? Now we only have to resolve one force. And this is the standard procedure for solving problems where we have a slope. It means that we resolve gravity, because gravity is always straight down towards the center of the earth. So we're going to walk through a little bit of a sort of mini geometric proof to do this. Here's my table. There's the angle that the table is making with the rest of the world. And there's my shifted axis. Now, what I'm going to attempt to convince you of is that the angle, whoops, here, so theta purple is the same as theta green. Here we go. Okay, I'm gonna move my purple over to right on the axis here. Can we all agree that this is a 90? Okay. So we know that this angle plus this angle also equal 90. Agreed? Wunderbar. Now, let me blow this up. If this angle and this angle equal 90, can we agree that that's a 90? Yes. Therefore, do this angle and this angle equal that 90? Yes. Therefore, this angle is equal to that angle. We good with that? You have two choices. You can be good with that. I can explain it again, or you can just accept it as an article of faith. It's really up to you. Some people choose, they say, can I come in after school because I just need to see that again? And some people are like, yep, got it, just going to accept it, moving on. It's up to you. The fact is they are identical. They are the same angle. And that's going to become really important because we're going to resolve gravity again and again and again and again and again. Okay, so I've redrawn this free body diagram. The reason I've done that, I'm going to go ahead and I can label the force of the table on the book. And that's force of table, that's 18 newtons up. And it's with our tilted axes, that's straight along the y-axis, no need to resolve it. I'm going to label our force of friction, which is also now straight along the axes, and that's to the left in our drawing. You could say uphill. We'll talk more about how weird that whole thing gets. But, okay. Now, I have the force of gravity on the book, which is 22 newtons. But this one now has to be resolved. So we've taken as an article of faith, or we've understood the geometric sort of mini proof, that this angle is 35 degrees. And I'm going to draw my f of g y and my f of g x on here. And that's a step we're going, like I said, we're going to take this step again and again and again and again. We're going to continue to resolve these forces. So f of gy, and here we've got y adjacent to our angle, so this is going to be fg cosine theta. Oops. And f of gx is going to be fg sine theta because it's opposing that angle. Well, that seems like a lot of work to do before we even do any real math. Okay, so my sum of forces on the x is equal to all of my forces right minus all of my forces to the left. A quick word here about signs. As this is drawn on a Cartesian coordinate system, is the force of gravity on the x positive or negative? On a Cartesian coordinate system, positive or negative? Well, on a Cartesian coordinate system, we usually think that this is positive and this is negative, and all we've done is tilt that, which would, okay, this gives me a headache for two reasons. Number one, it means that down the hill is positive, which I don't like. And number two, it means that gravity is positive, which I don't like. The important thing to understand is left and right, up and down, signs are just a proxy for direction. So we, by custom, sort of slap that Cartesian coordinate system on the whole wide world. We can modify that for our own convenience. Okay? So there's more than one way to skin this problem, is what I'm telling you. I'm going to go ahead and stick with our Cartesian sort of conventions, which makes it weird, but then at the end what we're going to do is use words to describe what's happening to the book rather than just relying on signs alone. And it's always good to remember that physics is actually applied math, so you have to understand what's happening in the world based on those signs and, you know, Cartesian conventions aside. All right, so sum of forces, on the x. What forces to the right do I have? Force of friction. What force do I have to the left? And that's, of course, to the right. Whoops. Oh, gosh. See, this is where that whole left-right thing really comes to bite me in the butt. Sorry. Force of gravity on the x. Let's try that. That's moving to the right. I can't really tell left from right all that reliably. It's sort of a 50-50 shot, which is the same odds you'd expect based on chance alone. So I'm not doing all that well. Okay. What force do I have to the left? I've got the force of friction. Yeah, and we can also use designations like forces up the table, forces down the table. We do that a lot because we have a lot of hill problems here. Okay, so what do I have? I got FG sine theta, and that's going in that direction, minus F friction. Okay, so I'm going to get my numbers. 22 times sine 35 minus 11. I have a sum of forces on my x-axis. It is 1.618 blah 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 newtons to the right, which means what? This thing is prone to moving to the right. Now, what I didn't do, and I probably should have done first, is check to make sure. I mean, you would think that they would mention something like this, but that the book is not crashing through the surface of the table or spontaneously floating up into the air. You never know. It could happen someday. Forces up minus forces down. What force do we have up? We have force of the table. What force do we have down? Force of G on the Y. 18 newtons minus, well, that's 22 cosine theta. Well, based on their terrible problem writing, I didn't write this one, folks. This book is sinking slightly down into the surface of the table. Gravity is exerting more force downward on it than the table is exerting upward on it. But that's because they expected that we would round at every step and it would all be 18 minus 18, so they got sloppy with their angle. They didn't mention that it was breaking the table. That's what happens when a table breaks. The force that gravity is exerting downward on an object is more than the force that the table can exert upward on it. I have a cousin who's he's a serial chair breaker. He's a huge guy. He's a bear. I mean, he's like 6'2", and he's like over 300 pounds, but it's all muscle. His dad, who was built just like him, used to entertain people by picking up engine blocks, just walking up to them and picking them up, because it's no big deal. They're just bears. They're enormous. And my dad spent every family holiday going, wait, no, don't sit on that one. Don't sit on that one. Wait, let me get you one. Let me get you a different one. And he breaks stuff. He's enormous. And he's not fat. He's just big. And it's like having Andre the Giant come over and sit on your little antique chair. The force that gravity is exerting on him is more than the force that the chair is capable of exerting upward on him. That's what would be happening in this situation, though that's just because of bad problem writing. So all the 4A problems are assigned. I think you probably have a few tilted axis, and then I will have the 4A worksheet for you tomorrow, and then we'll talk a bit more about normal force and force of tension, I think. So that's it.
4A worksheet assigned, or is it just like that?
It's going to be all.